All right. So remember, we're working on work. I had a couple definitions for work. First, that work was, or excuse me, it's not a vector quantity. Work is a scalar quantity, and work is equal to the dot product F dot D. We did the dot product. Remember, you just do it out like FOIL with the caveat that I dot I, J dot J, K dot K, that's equal to 1. Remember, because I and I are in the same direction, and you have that cosine theta term, cosine of 0 is equal to 1. And then anything that is orthogonal or perpendicular, like I dot J, is equal to 0. So you use that when you're doing your dot product, but otherwise it's just doing FOIL, first outer inner last. But then we also have the definition of a dot product is FD cosine theta, the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And remember, this comes about, the dot product is the product of two vectors, the product of the magnitude of two vectors. The component of one of those vectors is in the same direction as the other vector. And so if I have my displacement in this direction and my force in this direction, this is my angle theta. By doing that cosine theta term, I get F cosine theta. I'm taking the product of those two vectors, the displacement and the cosine theta term, the F cosine theta. So that's the purpose of a dot product, just the mathematical purpose, to multiply the magnitude of one vector times the component of the magnitude of another vector that's in the same direction. And we apply it in work. It comes up in a few other areas, though this is the only time we'll ever use the dot product. Yeah, it's the only time. The dot product is also called the scalar product. Remember, the result of a dot product is a scalar quantity. All right, let's try this quick test. This isn't meant to be difficult. You're just sort of plugging in numbers here. Want to know the work done by this shopper? She pushes a shopping cart at a 25-degree angle down an aisle. 25 or 60? Oh yeah, 60 degrees down a 25-meter length aisle. Use a shopping cart when you go shopping, Colin? Oh, reverse. Try this out. I use the force. Stop at 130. 130. All right, B is that right? Yeah, that is right. Very good. Guys, another thing that came up in the comments, more than two people said this, is just the pace of the clicker questions. I'm not going to change the pace of the clicker questions. I do want to just tell you that the purpose of the clicker questions is really just for you to come to class. That it's good for you to come to class, and students that have succeeded in the course in the past have regularly come to class. It's also just to sort of give you practice, quick practice, so that you can get really fast at working through these problems. Because on the quizzes, on the mini exams as we're now calling them, you really need to be fast. And this is the purpose of this is to help you build that speed, and also for standardized tests like the MCAT, what have you. But also, I just want you to understand the stakes for the clicker questions. That the stakes are pretty low. Like if you come to class regularly, you're going to get the full 50 points. In fact, I'll give you that if you come to every class and you don't have 50 points, you just come see me and I'll give you 50 points. All right, because you have to really be trying to not get the 50 points for class participation with the clicker questions. All right, it's really students that miss a lot of class that aren't going to get those questions. That aren't going to get those full points. All right. I think y'all, almost all of you are in a good standing for the class participation right now. You know what this reminds me of? This happened in my other class. Can I say it without offending y'all? Y'all aren't easily offended, are you? When it's B, what does this look like to y'all? Oh. Yeah. It's like you're giving me the middle finger. Oh. So whenever you all get the answer B, that's what it looks like to me.
I have a question on that one.
Yeah.
Okay, so it's a downward angle.
That doesn't matter.
It doesn't matter.
No.
So there's never a negative joules. There's never anything like that.
No, work is a scalar quantity, and the only reason you can have a negative work is if you're taking away energy. All right. So let me just sort of go through this quickly. My displacement is in this direction. It's 25 meters. My force is in this direction. It's 60 degrees below the horizontal, and my force is equal to 40 newtons. All right, and I just do work equals FD cosine theta. That F cosine theta gives me the force in this direction, and that's going to be 40 times 25, being a little loose with my sig figs, times the cosine of 60. It's 1,000 times a half, or 500 joules. All right. All right, so this is going to move us into the kinetic energy and the work energy theorem. First, kinetic energy is the energy that's associated with motion, and then the work energy theorem is going to say that anytime I do work on an object, I change its energy. And that'll be a really useful thing that we'll be able to apply in a lot of different scenarios. But first, let's just look at kinetic energy. Kinetic energy is the energy of a moving object. And it can be any type of object, like an alpha particle that's moving at relativistic speeds, an electron, a gas molecule, and in fact, I guess it's in PChem, and maybe in your introductory chemistry, you actually use energy and momentum to sort of build up this idea of classical thermodynamics. So thermodynamics, or thermal physics, is all built on the idea of the energy and momentum of particles, of gas molecules, for example. And y'all get into that, and I think we'll get into it a little bit at the end of this semester. Our kinetic energy is just equal to 1/2 mv squared. So it's proportional both to the mass of the particle and the square of the velocity. Now, for a long time, they didn't believe that the kinetic energy was proportional to the velocity squared. Instead, they believed that the kinetic energy was proportional to the velocity. Right? They didn't believe that it was proportional to the square of the velocity, because this was like in the 18th century, back in the 1700s and the 1600s. They didn't believe that because they thought that squared numbers were evil. I mean, you might think squared numbers are evil, right? But they literally thought that they were evil. Like, literally, squared numbers were unnatural, and that they were a product of Satan's work, these square numbers. Which, I mean, y'all might think that too, but I don't think that. I don't think that's true. But they thought this, and so they shied away from this idea of defining kinetic energy as the square of the velocity. Which is kind of silly, right? Yeah, it's a little bit silly, but can you think of a reason why they would actually use squared numbers? A lot. These people use squared numbers a lot, but they didn't really realize it. Why would they use squared numbers? People of the 18th century, 1700s. What do they do for a living, most of the people then? Huh? Well, a few people built stuff, yeah, and they use squared numbers a lot, but most people are actually what? Farmers. They're mostly farmers. They're largely an agrarian society, and so they use square numbers a lot, right? In what? Right, the size of the field. So they use that to calculate yields in their harvest, and to calculate, how many seeds they're going to need, or whatever, how much manure they need to spread on their field. So they use square numbers a lot. Now, there was a scientist then, a lady, Emily de Châtelet. She was in France. She was unique in the sense that she was a woman as a scientist, which was not very common back then. She was also quite a good scientist. She came about and she showed that instead the kinetic energy was proportional to the square of the velocity. And she did it by a fairly interesting experiment. Just take a moment to talk about it. She took a clay substance and she dropped a ball. And she dropped a ball so that when it struck the clay, this clay base, she knew what its velocity was, because they knew the kinematics equations that we covered in chapter 2. And then she measured the depth that the ball made in the clay. And so hitting at a velocity v, or speed v, she found that it made an indentation of a height h, or depth h. And then she dropped a ball from a greater height so that when it struck the clay, it had a speed 2v, had twice the speed of the original. Yeah, what's it? Clay? Like Play-Doh kind of thing? Like mud? Thick mud? Well, whatever.
Yeah,
It's,
I remember mostly mud.
it's sort of pliable, soft material.
Okay.
Like,
If you it's like if you go to Talbot in the back, you can see
Oh,
the hard part.
I got you.
Okay.
It's the pottery we just made out of.
Pottery is made out, although they fire it, make it
Yeah.
hard, right? So if the ball hits at 2v, how deep is the indentation going to be? Is it going to be twice as deep? It's going to be 4 times as deep, because the depth of the indentation is proportional to the energy of the ball, and it has 4 times the energy. And so she showed from this that, so this depth is 4h, and it's because of this relationship, because if I double v, that's going to quadruple the kinetic energy. You can do a similar experiment with the mass. You can increase the mass of the ball, and then you'll find that if you double the mass, you double the kinetic energy. I have a little clip about Emily de Châtelet. This is just an audio clip. It's just sort of a little interesting thing about her.
She was a brilliant young aristocrat, and her love affair would capture the spirit of the Enlightenment. But could be the plot for a period drama actually played out in real life.
The thinker Voltaire found a soulmate in Emily du Châtelet, pioneering scientist and intellectual. Author David Bodanis tells their tale and her story in the new book, Passionate Minds. Born in 1706, Emily du Châtelet was a bookworm when the king's own daughters were illiterate. She was a math whiz, and when she was sent to Versailles to find a suitable husband, which she eventually did, Bodanis writes that the 16-year-old found a way to fend off lascivious courtiers. She challenged one to a duel.
They went to one of the big buildings at Versailles, and she started taking her clothes off. Not all of them, just the equivalent of the petticoat layer. And it turned out she'd been a little bit of a tomboy as a child, and her father had given her fencing lessons and horse riding and shooting off to climb trees and stuff. So she didn't win the sword fight, she didn't kill the guy, but she didn't lose either, sort of a draw. And after that, she put down her sword, lifted up Descartes' analytic geometry, walked back outside, and the guys left her alone.
So ladies, if you ever want to get rid of like a quarter or whatever, you can just challenge them to a duel, right?
Yeah, that'll work.
Yeah. All right, so anyway, she was fairly important in this development of the idea for kinetic energy and what kinetic energy is. Let's try this other quick test. Remember, kinetic energy is 1/2 mv squared. I want to find the kinetic energy of a ball. It's 1/2 mv squared. Here I have a person throwing a ball at a certain angle. I want to know at the top of the ball's trajectory, what is its kinetic energy? About 10 more seconds. Stop at 150. Just guess if you don't know. All right. I think it's 123. What do you do if you get 123? What did y'all do?
Squared 35.
Okay. All right. So the answer actually is C. Let me show you why. Because remember, this comes back to our projectile motion. If I have something that's in this sort of path, and at the top of the trajectory, I want to know its velocity at the top, and the velocity is only the velocity in the x direction. So the velocity in the x direction at the top is equal to v naught times the cosine of the angle theta. So if I want to calculate my kinetic energy, it's going to be 1/2 mv squared, which is going to be 1/2 of my mass, which is 0.2 kilograms, times my velocity, which is v naught cosine theta, that's 35 cosine of 30 degrees, and that's squared. And then if I do that, I get 92 joules. So to find its kinetic energy, you just have to find its velocity, which is only going to be the velocity in the x direction. Even though we've moved past kinematics and projectile motion and Newton's laws and all that business, it will still come back in some of your questions, like something like this. All right, is this clear, guys? Let's give you just a second to finish that. We're going to move on and do some of the clicker questions. Have we started the clicker questions for this chapter? Can you go away from there? All right, I'll come back to it in a few minutes. All right. So, is it possible to do work on an object that remains at rest? Yes or no? Stop at 20 seconds. 5 more seconds. Okay. All right, remember work is equal to force times displacement. Work is force times displacement. So let's just try it one more time. What does it mean for those things if I'm at rest for one of those? Work is force times displacement. Stop at 17. Okay, very good. If I'm at rest, my displacement is 0, right? Because it's not changing position. So that's going to be B. Very good. A box is being pulled across a rough floor at a constant speed. What can you say about work done by friction? Is it no work, negative work, or positive work? Remember what we were talking about? If the force and the displacement are in the same direction, it's positive. If they're in opposite directions, it's negative. If they're perpendicular, it's 0. Stop at 45. Very good. It's B. And the reason for that is that almost always our kinetic frictional force, our static frictional force, or whatever, our frictional force is opposite the direction of motion, and that's clear in this case that it's opposite the direction of motion. So I have a box, it's moving in this direction across the floor, so my displacement is in that direction. but my kinetic frictional force is in the opposite direction. So that angle theta is 180 degrees, and so the work is negative. But remember, guys, negative work does not mean that it's a vector quantity. The negative means what? Not in the opposite direction.
It's slowing it down.
It's slowing it
It's
down.
going against.
Right, it's going against. It's actually taking away energy is what we'll, in the next section, we'll talk about that. That it's a dissipative force. It's taking away energy. All right, can friction ever do positive work? The answer to this is yes. I'm going to put in A. What?
I just thought it was funny because you just gave a chance.
Why?
We got a 50-50 shot.
The answer is
You
yes.
just assumed that we were gonna get it wrong.
Well, we just said that friction is almost always negative, but here I want to show you an example where it's not, where it's positive. There aren't many scenarios where it is positive, but in this case, let's say that I have a truck, for example.
Nice job.
That's a nice one, isn't it?
Kind of looks like my car.
My little boy loves trucks. Like, that was his first word, truck. And so my wife and I got pretty good at drawing trucks. So let's say, what's that?
You say that low.
Truck, yeah. All right, so if I have a box on the back of a truck, the displacement is in this direction, all right? But the frictional force is also in that direction. That frictional force is actually what keeps it on the back of the truck, because if it wasn't there, it would slide off the back due to its inertia. So that's one scenario where you can have positive work done by friction. All right, in a baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? Positive, negative, or zero work? So the catcher exerts a force on the ball. Is that force do positive, negative, or zero work? Since I've already offended half of you with the finger on the, or y'all did that, not me. But let me tell you an offensive joke. Is that okay? Huh? Well, if you're offended already, just might as well get it all in on the same day. All right, so knock knock. Smell mop. Thank you. No, I don't want to do that.
Come on.
I already got the drill.
Huh? Did y'all get it? Yeah. All right, I'm gonna stop this. All right, so the catcher's done negative work. All right, because the catcher is exerting a force on the ball in that direction, but the ball is traveling in this direction. So it has opposite directions, so negative work. Or you can think of it as Scott said earlier, that the catcher is taking away and slowing down the ball, and so that's also negative work. We'll formalize that in the next section. We're going to skip this one. All right, you lift a book with your hand in such a way that it moves up at constant speed. While it is moving, what is the total work done on the book? The net work, if you will, which is the sum of all the works done by the forces. The answer's not F. My first year I gave an exam in my other class. It was all multiple choice, and one of my multiple choice questions I had like 12 options on. What's that, Jose?
Is it close by?
Yeah, it's all right.
All right, I'll stop at 50 seconds. 50? All right, D is right. Good. Let me show you why. I have a certain amount of work that's being done by this force, and that work is equal to the force of the hand times delta R. And then I have a certain amount of work done by this force, or this is cosine of 0, which is equal to 1. 0 degrees. And down here I have the force weight times delta R times the cosine of 180. All right, so I have two equal forces, equal but opposite forces, and equal but opposite forces. So one is positive and one is negative, so they go away. You could also just think about its net force. Since it's moving at a constant speed, that means the acceleration equals 0, and so the net force equals 0, and so the net work is also going to be 0. By what factor does the kinetic energy of a car change when its speed is tripled? I think Emily de Châtelet, what would she say? Right, if the speed is tripled. Stop at 40 seconds. D is the right answer. Remember, it's a quadratic relationship. So if I double the velocity, I quadruple the kinetic energy. So if I were to plot kinetic energy versus V, it's a parabola. It looks like that. So as I move up to higher speeds, I get a greater increase in my kinetic energy. So it's D is a factor of 9. Car number 2 has twice the mass, or car number 1 has twice the mass of car number 2, but they have the same kinetic energy. How do their speeds compare? When you encounter problems like this, I find it useful to write out the equation. 1/2 mv squared equals 1/2 mv squared, because I know their kinetic energies are the same. And then I say, well, I double the mass over here. So what has to happen to the velocity on the other side, or the speed, to make those equal? If I double the mass on the left-hand side, they're no longer equal. Stop at 120. 120. 5 more seconds. All right, B is the right answer. Let me show you. So if I double the mass right here, in order to make the right-hand side still be the same, I have to double this term. And so that's going to have to put in a square root of 2, because square root of 2 squared is equal to 2. The ability to look at relationships in that way and think about how if you change one variable, how does the other variable change, is very important, and that's good fodder for standardized tests. So if you're taking the GRE or the MCAT or something, you really need to know how to do those sorts of things. All right, 2 stones, one twice the mass, are dropped from a cliff. What is the kinetic energy of a heavy stone? Stop at 45. Okay, let's try it again. Just going to remind you the equation for kinetic energy. It is either D or E. Kinetic energy is equal to 1/2 mv v squared. And what I'm asking is, if you double the mass, what happens to the kinetic energy? That's what's happened here, right? That it's twice the mass. Because when they reach the bottom, what's up with the velocities? How are they different? They're equal, right? You drop two objects, regardless of the mass, they're going to accelerate at the same rate. So try this again. Stop in about 10 seconds at 25. I'll go to 30. All right, so the speeds are the same, right? When they get to the bottom, the speeds are the same. So the v is going to be the same for both of them. So the only thing that we're changing is the mass. All right, so that means that if you double the mass, you're going to double the kinetic energy. Yeah? Every answer is okay. I mean, some are right, some are wrong, but everything's
Every answer. You're kind of convincing yourself. Some are more.
But we're accepting of all answers, even the wrong ones. But you don't get any credit for the wrong answers.
Some answers are more okay than others.
Okay, so what is the final speed of the heavy stone compared with the light one? How do they compare?
Didn't you just say that?
Hmm?
Didn't you just say that?
That is just it, yeah. So I'm at 25. Somebody else says that'd be funny. Did I mark it? Did I mark it right? Yeah. All right, so if you drop them, they're going to have the same speed at the bottom. They accelerate at the same rate. Okay, just a couple more. A child on a skateboard is moving at a speed of 2 meters per second. A force acts on the child. Our speed is 3 meters per second. What can you say about the work done by the external force on the child? Positive, negative, or zero work? We'll make this our last one. We'll move back to something else. Just a few more seconds. Very good. The force is in the same direction as the displacement, and so it's going to be positive work. But we can also think of it as, which we'll get into now, the work energy theorem. The work energy theorem says that if you do work on an object, you increase its energy. Or if you do negative work on an object, you decrease its energy. In this case, we're doing work on this object, and we're increasing the child's kinetic energy, and so that is positive work. But you know, let's do this one. A car starts and it from rest accelerates to 30, and then later it accelerates to 60. Which takes more energy, 0 to 30 or 30 to 60 miles an hour? Is it starting from rest or starting at 30 and going to the higher speed? stop at 35. All right. Let's try it again. I'm going to plot, though. I did this before. If I plot the kinetic energy versus the speed, remember kinetic energy in v squared, it looks like this. It's a parabola. And so, which requires more energy? Going from 0 to 30 or 30 to 60? Which of those requires more energy? Stop at 30. Okay, it is B. Notice it takes a lot more energy to go at higher speeds. And not just because of the wind resistance. Though as you move faster, the wind resistance is a lot bigger. But it's just because of the fact of the energy required is more. Yeah.
You also kind of like gain mass when you go faster too, forward.
No, I mean not at slow speeds. Yeah. All right. So, yeah, at relativistic speeds. Yeah. But you're not going that fast. All right. If y'all remember, actually, remember we had this when we did the drag race problem. Y'all remember that problem with the Lamborghini and the little Subaru? When we plotted, I don't know if you recall that we plotted the velocity versus time graph, and remember we decided that it wasn't a linear graph, but instead the cars were traveling like this, and that's because of this fact that as you go faster, it requires more and more energy. So the cars, as they go faster and faster, their acceleration actually tails off. They begin to accelerate more slowly, just because it requires a lot more energy to go at those faster speeds. All right, we'll just do a couple more. Is it possible for the kinetic energy of an object to be zero? Or negative, rather? I will tell you that kinetic energy is a scalar quantity, just like work. All right, but is it possible for it to be zero or negative? Stop at 28.
I say that anything is possible, is that correct?
Okay. The answer is no. I mean, mathematically, with the work, we had this ability to make it mathematically to come out negative, but you don't have that with kinetic energy. Right? There is no cosine term. Even if you did include the sign of the speed, that sign would go away. You can't have a negative mass. So just mathematically, it doesn't work out. And in fact, it doesn't really mean anything to have negative energy. Okay? Not anything is possible. Some things are possible, but not negative kinetic energy. All right, let's stop there. Which problem number is that? 27. Let me write this down. We'll probably finish those up on Friday. We'll probably finish this chapter, in fact, on Friday. All right, so let's move on to the work energy theorem. This is pretty simple. I've already stated it, but it just says that if you do work on an object, that you change its energy. We usually look just at that you change its kinetic energy. So like if I do work on this chair, I push it, then I change its energy. I give it kinetic energy. I set it into motion. But it's also true that if I do work on an object, I can change its potential energy, and we'll get into that in just a bit. But like if I move this object, I apply a force to it, and I move it up to a higher position, then I've increased its potential for motion, because if I let it go, then it falls at a faster speed when it gets down to the bottom than if I drop it at a lower position. All right, so if I do work on an object, I exert a force over a displacement, then I can change its energy. So if you do positive work on an object, you increase its energy. And if you do negative work, you decrease its energy. All right, so I remember the catcher catching the ball. That's doing negative work. He's slowing the ball down and taking energy away from the ball. Or like pushing the chair aside, that's a positive work, which increases the energy. What? Let's look at conservative and non-conservative forces. So these are two classes of forces. We have lots of different classes, it seems like, right? Like different types of forces, but these are two types of forces. A conservative force is a force that conserves energy. So that is the amount of work done by the force. The amount of work done by the force changes the energy by the same amount. A good example of a conservative force is a gravitational force. All right, so for example, if I have this object up here and I have a gravitational force that's pulling it down, that's causing it to accelerate at a certain rate. And so if I let it go, that force does a certain amount of work on the object as it travels from here down to the ground. Just before it hits, all of that work that's been done on the object, the force of gravity times the displacement, all that is converted into kinetic energy. So all the work done by the gravitational force at this point, as it moves downward, is all converted to kinetic energy when it reaches the bottom. Yeah.
If you drop it something, wouldn't that be negative 9.8 if you're using that for gravity? So would the question technically work out to be negative then?
No, let me draw a picture for you. So if I have an object and I'm dropping it a certain distance, it has a force, the force weight, and it has a certain displacement. Right? Both of those are in the negative direction, but it doesn't matter. You really don't want to know the magnitude of one force times the magnitude of the other force times the cosine of the angle between them. So it's that angle that gives you the sign. And in this case, since the sine is 0, the cosine of 0 is positive 1, not negative 1. It doesn't matter that they're both in the negative direction. What matters is that they're both in the same direction. Does that answer your question? Yeah. All right, so if I have this, and since the force due to gravity is a conservative force, I can say that work is equal to force times displacement. And then when the ball reaches down here, the kinetic energy is equal to 1/2 mv squared. And I can set those two equal. The force times displacement equals 1/2 mv squared. I can only say that because it is conservative. It's a conservative force. All field forces are conservative. So electric forces are also conservative, and we'll use that fact next semester to develop some ideas about energy, electrical energy. And most other forces are not conservative. What is it about field forces that allows them to be conservative? That they don't lose energy?
They're constant?
No, what'd you say? They're non-contact, right. So you don't have contact between surfaces, because anytime you have contact between surfaces, you lose energy. You don't conserve energy. Right, and so non-conservative forces don't conserve energy. And we'll wrap up with this next blank. Friction is a good example. Basically, any contact force is an example of a non-conservative force. So sometimes we'll have contact forces and we'll estimate that they are conservative, but really they're not, because anytime you have contact between two surfaces, you lose energy. All right? Guys, I just want to say one other thing, too. Some of you commented about the videos and stuff. I think the videos are great. Like, they're a great way for you to get extra practice, but I want to warn you that it's not really something that will help you if you just watch them, but they're really meant to be as a sort of a last-ditch resort. That as you're working through the homework, if you encounter a problem and you can't come see me or whatever, or you don't have a friend there to help you, then you can go to the videos and see where you're stuck. Okay, so that's really how they're intended to be used. Same with the old exams. Just watching them over and over. I don't really find that really helps a whole lot. It's really putting your pen to the paper and practicing in that way that will help you.
I didn't get to the English one, I got completely lost. I'm like, okay, I have no idea how to do it.
That's okay.
Show me.
Yeah, y'all have a great day, okay?